So we have a problem called reconstruction. Reconstruction is that I have a signal, it's already sampled. Suppose that is not a quantized signal. We have a discrete time signal. It's only on the x-axis, not on the y-axis. So it's a sample signal. I want to make it back to the analog signal, xt. How to do that? In an ideal case, ideal reconstruction, we know we need to do a low-pass filtering. So if this is a frequency, digitized, I have something like this. In the middle, that's my xf or x omega. And here is xf subtract fs. Here is xf plus fs. And you have other copies. For reconstruction, in the frequency domain, ideally what we do is we filter that using a low-pass filter, which is ideally a rectangular function. And then let's see what will we have in the time domain. So for this reconstruction, we have h omega, which is my rectangular function, right? H omega, h pi, hf, that's the same. H omega is 2 pi. That's just the frequency variable. So h is a function of a frequency. And this is my, this is my hf or h omega. This is my rectangular box. So rectangular function is, we have a t0 when this omega is from negative pi over t to pi over t. And that's otherwise. Otherwise, it's all 0. Okay. Yeah. This is according to the sampling theory. 1 over t is fs. So we have the omega is 2 pi f. I want to have this point. This point is fs over 2. This point is negative fs over 2. As long as I'm in this range, I can have this pass. Later on, we will know what we need to do in the time domain is we need to move this rectangular box, or we call it a filter, or the system. It's really a reconstruction. It's a low-pass system. You go through the system, and then you only have this low-frequency component. The system itself using t or using h to represent. So this is h in the frequency domain. Come back to the h in the time domain. We are using an inverse Fourier transform, and then we will know later about this mathematical format. But let's just give a brief look at it. It's my h omega times e to the j omega t d omega. So it's integration. This is my frequency domain function multiplied by this term e to the power of j omega t d omega. So that is 1 over 2 pi. Since h omega is a rectangular function, it's very simple. I only need to limit on my integration. So it's negative pi over t to pi over t, and that's t e to the j omega t d omega, right? Only in this range, I got a constant value t. Other than that, it's all 0. So I have changed that to the integration in this range. And there, this will give me, continue here. To calculate this integration, eventually it will give us a sine function, sine of pi t over capital T. And we have pi t here. And that is our sinc function. This is our sinc t over capital T. Well, here the sinc, let's sinc y, sine of pi y over pi y. This is my sinc function. Okay, it represents here. Okay, so we know from signal system that indeed a rectangular box you translate into the frequency domain, or on the other vice versa, from the frequency domain translate to the time domain, a rectangular function becomes a sinc function. Then what we need to do to find the reconstructed signal, this is reconstructed signal, is my sampled signal convolved with ht. What does that mean? Well, S sub S, that's a signal look like this. Okay, I'm just try a few of those. That's the sampled signal, XST, convolved with rectangular box. Well, in frequency domain, you multiply the rectangular box. In time domain, you convolve with this sinc function. Okay, that's exactly what we are doing here. We low pass that. So replace that with my value. So this is xk delta t subtract kt. Okay, from negative infinite to infinite. This is what we did before. That's how we do the sampling. Sampling is for these are each value, x0, x1, x2, each value, and we multiply by the delta string. So that gave me a kind of a continuous waveform. I only take this a non-zero value. In between, I'm padding all zeros. That's what it has. Padding all zeros. That's what you do with the delta function. And the same thing here. So it's a delta string. And this one is then convolved with ht, where ht is a sinc function. I just calculated. So that is a convolution is a integration of this part of k from negative infinite to infinite xk delta t subtract kt. And let me change a little bit. So I change this variable to tau, and then ht subtract tau d tau. By just those two parts, the first function t becomes tau, the second function becomes t subtract tau. T is the convolution, this entire t here, and then the integration over tau. Change the order of summation and integration. So integration bring into the inner part. xk, k is nothing to do with tau, so we can bring that out. So you have here is integration of delta tau subtract kt multiplied by this. And then we know the integration of delta of anything, and then we just simply put this ht subtract kt. Okay. So this part is integration of delta h. So eventually we will find out the reconstruction formula, and this is the final result that I have here, is xk. This is each point, discrete time sample point multiplied by this. That is my sinc function, sinc of t subtract kt over t. Okay. So it is a sinc for each of the point here. You just kind of multiply by a sinc function, another one multiplied by a sinc function, and then you're adding together, and that will give you the reconstructed signal. This is exactly equal to your original analog signal. If you do this, the low pass filter, the condition is here. You can do this. You can do this following the Nyquist rate. Okay, so let me write it here. This is the reconstruction formula. Maybe you like to write it down, but all we need to remember is that this is a convolution, and what we do is, so each point multiplied by the sinc with some delay, and then we sum it together, and we have the reconstructed signal.